Greetings everyone, we're going to be talking about momentum and work in two dimensions. Here's a sketch of a box on a ramp, and here we've labeled our different forces. So our key forces here to keep in mind are, of course, gravity, mg, and the frictional force on the box. These are the only two forces on this box, but as you see they don't line up very neatly. So we're going to talk about ways in order to make this problem a bit more easily solvable. But first let's talk about the vector dot product, or the scalar product. So let's take two vectors A, and then we're going to multiply them together. So this multiplication, A dot B, we talked about how to do this. So if A is AX x hat plus AY y hat, and B is pretty similar, bx x hat plus by y hat. If we were just adding these, we do a plus b, then we're going to get ax plus bx x hat plus ay plus by y hat. But here I'd like you to consider this dot product, and so instead of adding these, what we're going to end up doing is multiplying the two x hat components together and the two y hat components together. So this is going to be ax bx plus ay by. And the big difference here is that when we added them, well, what we're doing is saying, well, here's a, and then now we're going to add on b, and so we're going to get some vector c or something. And c is also a vector. When we do the dot product, we're going to end up getting a scalar, and that's why this is called the scalar product, because this is a way of multiplying vectors and it gives you a scalar. So this is just a number here. There's no direction here, so this is just a number. And what this number is it tells you the projection of b onto a, or a onto b. Basically tells you how much is one of these vectors in the direction of the other one. So that may sound a little confusing. So let's make another example. So let's take two vectors, and in this case we're going to be using a unit vector. Unit vector is a special vector that the magnitude of it is 1. So x hat is actually a unit vector. So if we looked at the magnitude of x hat, that would just be 1. So here's the x hat direction, and here is the y direction. So we're going to take a vector A right here. And what I want to know is, what is A dot x hat? And what this will give me is the projection of A onto x. So if you imagine here, maybe you could tilt your coordinate system something like this. Maybe call this x, this y, and now we're doing like b dot onto x. So it tells you the amount of b that's in the x direction. So what this is going to give you is just ax. So the other important thing about this scalar product is that there's two different ways to calculate it. So this is one where we multiply the x components together and the y components together, and then it gave us this projection piece. But there's another way to calculate this, and that's a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. So here we can imagine theta. So here if we have two vectors and say that this angle is 30 degrees or something like this, we could look at A, we could look at B. Maybe we knew the length of A was 4 or something. Maybe this is 4 meters long. Maybe B is 3 meters long. So then A dot B would be 4 times 3 times cosine of 30. So another thing that is useful here with this dot product is that you can use this dot product to find this angle. So let's do some examples. Let's say A dot B is equal to 3 times 4 plus 4 times 3, and this is going to give you 24. Now we could work out this dot product the other way. Look at the magnitudes. So this is a 3, 4, 5 triangle, so that's 5 times 5, and then now times cosine theta. So now we can use this to find what theta is. And so here we're going to get 24 over 25 is going to give you cosine theta. So then doing the arc cosine of 24 over 25, this is going to give you theta. Be careful because when you plug this into your calculator, make sure it's in degrees or know how to convert between degrees and radians. So if you have radians, a real easy way to convert between radians and degrees are to multiply it by 180 over pi. So if you look at a circle, right, then we know that there's 360 degrees in a circle, or 2 pi radians, or you can just look at the half circle. And so there's 180 degrees there, and that's just pi radians. So you could take the result of this and multiply it by 180 over pi to give you degrees. So let's do another one. Here we got A dot B, and in this case we're going to get 3 times 4 plus 9 times minus 1. So that's 12 minus 9, so that's just 3. And then now let's look at the magnitudes, which you'll get when you take the magnitude of A is 9.5, so just use Pythagorean theorem. And then the magnitude of B is going to be 4.12. And then that's times cosine theta. So solving for cosine theta, you'll see that this is equal to 3 over 39. And so then theta is going to be the arc cosine of this 3 over 39, or about 86 degrees. So we can double check our result by just drawing these two vectors. So here we have A is 3, 9, so it's up like this. And then B is 4 minus 1. So you can see that this angle between them is almost 90 degrees. This is 86 degrees. And that's why when we took the projection of A onto B, we got such a small number, even though their magnitudes are pretty big. So then getting the angle between two of these vectors to be 90, cosine of 90 is going to give you 0. So that's why when we look at, maybe y dot x, this is going to give you 0, because the angle between these two is 90 degrees. All right, so let's use our 2D vectors in order to solve some problems. And here we're going to be doing a couple of free body diagrams, and then we're going to end up on a momentum problem. But for all of these, what we've learned in class is pretty much going to stay the same. Here we're going to be just looking at some of our forces, but here instead of just having one direction, we're going to have two different directions that we have to think about. So we need to sum up our forces in x and the y direction. So let's go ahead and draw some of the forces on here. So here I have a sign, it's suspended. I need to draw gravity on here. And then there's two wires. So these wires are going to be pulling on the box. So there's this one force, maybe that guy's T1, and there's this other wire pulling straight out to the sideway. And that guy's going to be T2. So here is my free body diagram. That's all my major forces. But one thing kind of sticks out, and that's this T1 is not really in line with either of these two guys. These guys are nicely perpendicular, but this guy, we need to decompose him into our x and y coordinates. So maybe this way is y and this way is x. So then we need to decompose this T1 and get T1x and then T1y. So we can go ahead and look at T1x. That's just T1 cosine of this 30 degrees. And then T1y is just T1 sine of this 30 degrees. So the sum of all of my forces in the x direction are going to be this T1x and then minus T2. So T1x minus T2, and the sine, its acceleration is 0. It could be moving at a constant speed, that would be fine. But the acceleration of this object is 0. So that's just going to be 0. And then now we're going to have our y direction. So here we have, in our plus y, we have T1y. So that's T1y minus mg equals 0. So I need to plug in a few things before I can solve this, because right now I have 1, 2, 3 unknowns and only 2 equations. So I need to plug in these guys. So here's equation 1 and 2. So into 1, I'm just going to substitute T1 cosine 30 degrees minus T2 equals 0. And then into 2, I'm going to have T1 sine of 30 degrees minus mg equals 0. So I can go ahead and find T1 pretty easy. So T1 is really just mg over sine 30. And I'm going to get 98 newtons. So this is just using equation 2. And then I can use equation 1 up here in order to solve for T2. So T2 is going to be T1 cosine theta. So T2 is T1 cosine theta. So then T2 is going to be equal to 85 newtons. Alright, so now let's consider this block on the ramp and how to decompose these forces into a nice coordinate system. So here I have mg pulling me down, and I know that I'm going to have some normal force. This normal force has to be perpendicular to the surface. So this is my Fn. So these are all the forces on the block. I've already kind of solved this problem. I haven't really solved out what Fn is. I also have, if there's friction, then I'm going to have some frictional force opposing the motion that this block wants to slide on. So let's go ahead and find out what this Fn is and what is this frictional force. So in order to do this, I'd like to have everything in these orthogonal. By orthogonal, I mean they need to be 90 degrees to each other. So this is like x and y. So here I have two vectors that are already at 90 degrees. So that already makes for a nice coordinate system. So let's go ahead and make this way x and this way y. So I have kind of rotated my coordinate system so that x lines up with the slope of the ramp. But now mg down here doesn't line up into this nice coordinate system. So what I need to do is to split it up into two pieces. A piece that's in the x projection and the piece that's projected along y. So what I'm doing is doing this y component plus this x component, so connecting these head to tail, has to give me back mg. So I have to draw the triangle this way. So I need to know what this angle is. And what I can do is that gravity is straight down, this is 90 degrees, so this angle up here it has to be 60. This angle right here has to be 90 degrees, so then this is 30. So this angle is the same as this angle. So now I need to come up with what are these two pieces. So now that I have mg as my hypotenuse, I can look at this guy and go, that guy should be mg sine theta, and then this piece right here should be mg cosine theta. So I've decomposed this mg into two different pieces that are projected on this x and y coordinate system. So let's look at the sum of my forces in the x direction. So in the plus x, I have mg sine theta. And then in my minus x, I have this friction, so minus ff. And then let's say that the box is at rest, so acceleration is 0. And let's do the same thing for y. So in the y, I have my normal force minus this piece right here. So this is mg cosine theta. And this is equal to 0. So right away I could go ahead and find out what Fn is and Ff are going to be. So my frictional force, if this guy is at rest, is going to be mg sine theta. And my normal force has to be mg cosine theta. So if you want some numbers here, you can find out that the friction force has to be 9.8 newtons, and this guy is 17 newtons. So here we have the same basic diagram, and I'm going to just redraw it again just to let you see that. But this asks us a little different question. It says, what does the coefficient of friction have to be for this block to have a constant velocity? So the block is moving at v constant, which means that a is 0. So when I sum up these forces again of fx, I should get 0. So here I still have mg, and I need to split this up into the two components again. So I can remember that this angle is theta, or 30 degrees again. And so then this part is going to be mg cosine theta, and then this part is going to be mg sine theta. Here's my normal force, and then here's my frictional force. So the other thing I need to recall is that friction force is equal to mu Fn. So let me kind of box that guy in to separate it a little bit. Alright. So here I've decomposed all my forces, so I can go ahead and look at my x and y direction. So here's x, here's y. In my x direction, I'm going to have mg sine theta minus my frictional force. And then when I look at my y direction, I'm going to have Fn minus mg cosine theta. And so I can go ahead and say, well, Fn has to be this mg cosine theta. And I know that my friction force has to be sine theta. But friction force is also equal to mu Fn. So this guy also has to be equal to mu times mg cosine theta. So let's solve for that mu. So that mu is going to be mg sine theta over mg cosine theta. So this is just sine theta over cosine theta, which is just tangent theta. So for it to slide down at a constant velocity, this coefficient of friction has to be equal to tangent theta. And so I could solve for mu, plugging this in, and I'm going to get 0.577. So now let's look at the work that's being done on a box. So this box is going to slide at some constant velocity, so that means that A is 0. So let's look at the forces that are on this box. We have mg again. We're going to split this up into the two pieces, mg cosine theta, and then mg sine theta. So we have the normal force, and we have the force of friction. So here we want to know the work that's done on this box due to two pieces. We can recall that the total work done is equal to the change in kinetic energy. But since this box has a constant velocity, this is going to be 0. The kinetic energy isn't changing, so the total work is 0. But we're splitting this total work up into two different pieces. friction is doing a force, is doing work on this box, but that's being countered by the work of gravity. So the work of friction is going to be the frictional force dotted with the displacement that the box goes. So this box is being displaced some x down the ramp, this 2 meters right here. So this dot product tells me that if I know the magnitude of the frictional force and I know the magnitude of the displacement, I can talk about the cosine of the angle between them. So I'm just going to go ahead and draw my frictional force here and then my displacement here. So the angle between these two, I'm going to call that angle phi, and that's 180. So here, cosine phi is going to give me a -1. So when I plug this in, the work of friction is going to be mg, and I can use what I learned in my last slide, sine theta times d, which is this 2 meters, and then times this cosine phi, which is going to give me this -1 because the force of friction is opposite direction that this displacement is going over. And I can find out that this is going to be -34 joules. So the thing to be careful about is what this angle is and this angle. Don't mix these two guys up because they're really different. This is the angle of the ramp, and this is the angle between these two vectors. So let's find out the work that's done by gravity. So this is the force that gravity does. So here we can look at mg is this way, right? So gravity is just mg. And then now we're going to, so the magnitude of that guy, and then times the 2 meters, and then now times cosine of the angle between these two guys, right? So the angle between this and this is this 60 degrees. And when I plug this in, I'm also going to get 34 joules. Alright, so let's do one more box on a ramp problem. I know you're probably sick of these already, but they're good practice for drawing these free body diagrams. So let's go ahead and draw our forces again. mg cosine theta, mg sine theta, where this is theta. This is my normal force, and then friction, wait. And then before I go any further, let's take a closer look at this problem. So we're going to shove the box. So before I go any further, let's read this problem a little bit more carefully. So we're going to shove the box up the ramp. So we're giving the box a velocity this way. So that means frictional force is actually this way. And so the speed has an initial velocity v, and the kinetic friction between the box and the ramp is mu k. How far up the ramp does the box go? So let's go ahead and sum up our forces in the x direction. So in my x direction I have, well, nothing, and then I have a minus my frictional force, and then minus mg sine theta, and this is going to be equal to ma. In this case, I know that when I shove the box up, there's no forces in the direction of this. I could be pretty sure that a is not going to be 0, because here friction goes this way, mg goes this way. Nothing really is pushing this box up the ramp. It just has a velocity to carry it up the ramp. And so it's going to be slowing down, so the acceleration of the box is actually going to end up being this way. So I better get a negative number here for my acceleration. So in the y direction, we have a bit easier time here. So my normal force minus mg cosine theta, and that is equal to 0. because the box is not accelerating in this y direction. So I know that my normal force, again, is just equal to mg cosine theta. So how far does the box make it up the ramp? What I really want to know is, initially I have some amount of kinetic energy, because the box has a speed v, right? This is 1/2 mv squared. And then friction and gravity are going to do some work on this box. So then the work that's being done is the change in kinetic energy. And the work that's done is the net force times the distance. So this is my net force in this x direction. So I actually have I have force of friction plus mg sine theta, and then times the distance that it's going up the ramp. So let's call this direction d. This force times distance has to be equal to the work, which is equal to 1/2 mv squared. So what I really want to do is solve for this d. When I solve for that d, I'm going to get 1/2 mv squared all over force of friction. Friction is, this guy right here is equal to Fn mu times Fn. So I can go ahead and stick this in. Mu times Fn, which is mg cosine theta, plus mg sine theta. And then this is going to be how far the block goes up the ramp. It's going to really depend on this gravity. It's going to depend on the angle. It's going to depend on v. But it doesn't depend on m. M's all cancel. So if the static friction, this really should be mu s, is mu s, then what's the max angle of theta for the block to go up and then stop somewhere? So what this really means is that you're going to push this box, it's going to slide up the ramp, it's going to go up some d. This d depends on mu k, because the box is moving at this point, so that's our kinetic friction. When it gets to the top of its trajectory up this ramp, it's going to have some time which v is 0. At that point, we have static friction. And so we already worked out that friction is equal to this tangent theta. And you can go back a few slides to see how we found this coefficient of static friction is equal to tangent theta. And that's not going to change for this either. And so we're really just solving for this max theta. So what we want is this theta to be equal to the arctangent of mu s. Now if theta is smaller than this, that's okay, because we're going to still have enough static friction. But if theta is any bigger than this value, then the block will slide down. Alright, so enough of free body diagrams in 2D. Let's talk about momentum. So we're going to go about things pretty much the same way. We're going to draw a picture, label our origin, look at our plus x and y axes. Then we need to label everything on this picture. We need to label velocities, masses, and then think about what's happening initially and finally. Then, this is really important, we should mark out what we'd like to know. This is going to help direct our algebra. And then we need to write out the sum of our momentum. So with free body diagrams, we kept doing sum of forces, but here we need to do sum of momentum in x and do sum of momentum in y. And this will be conserved. Then we just solve for what we'd like to know. So let's do a problem. In this problem, we have a blue car. That's this guy. He has a mass mc, and he's traveling at 10 meters per second to the north. So this is VCI. He's going to pass through an intersection, and there's also this red truck, and he's got VTI, and he's moving to the east. So after they crash, they crunch and skid off together. So this tells me that this is an inelastic, totally inelastic collision. So what is their velocity after the crash? So here I have MC, MT, and then after the collision, let's change color to green or something. What I'm going to get is some mass here, and it's going to be moving off. And I hope it's going to be moving off this way, because that's what my intuition tells me. And so what I want to do is find this velocity. So what I need to do is work with my momentum in the x direction, and work with my momentum in the y direction, and let's see what we get. So in the x direction, initially, I just have the truck. So that's MT VTI. And the car doesn't have any momentum in this x direction. But the wreck, when they both collide together, this wreck has to have some momentum. So that's our MT plus MC. And then this is going to be V final X. And then I need to do the same thing for my y direction. So here I have MC, MCI is equal to MT plus MC V final Y. So now what I'm really doing is, I should say, what am I after? I'm after this final velocity. So what I'm really solving for is these two guys. So V final X is going to be VT of the truck initially, and then now this ratio of these two masses, the mass of the truck and then the combined mass. And what I'm going to get is 6 meters per second. And I do the same thing in the y direction, and I'm going to get V car initial, M car over the combined masses, and I'm going to get 4 meters per second. So what is the velocity? So I haven't quite solved for that. I solved for the components of the velocity, but what I'd really like to know is what is V. I can even solve for what the angle that they go off at. So this is V final X, and then this is V final Y. So if I want to solve for V, well, I could write it out in component form, or I could write it out in my polar coordinates. So solve for the magnitude of V, and I'm just going to do Pythagorean theorem, square root of 4 squared plus 6 squared, and I'm going to get 7.2 meters per second. But then velocity is a vector, so I also have to have a direction. So this is at 39 degrees north of east is how I could kind of say what this angle is right here.